Hi, folks. Welcome back. Hope you all enjoyed the guest lecture last Thursday. So today we're going to continue our discussion about multimodal reasoning. So LP already gave a little bit of a glimpse on how we can do reasoning through graph neural networks and the like. We'll continue discussing reasoning today. To recall, reasoning is all about how do you combine knowledge. How do you combine knowledge in a principled, in a structured way that is ideally interpretable by us humans in order to solve the problem. And as a roadmap, recall that in the first couple of weeks, we looked at local representations. If you have one element from modality A and one element from B, what are the different ways you can learn representations, either through fusion, coordination, or fission. Right? But we only looked at one element from A and one element from B. In the next couple of weeks, we looked at the case where there are multiple elements with some structure within each modality. For example, multiple words in a sentence, along with multiple image regions in an object with respect to some spatial structure. So given these multiple elements, we looked at how we can learn aligned representations. How do we learn the alignment more generally, but also more importantly, how can we learn representations that take into account the fact that different elements are aligned with each other? And we talked about methods such as transformers, such as attention-based methods to capture these alignments through attention and self-attention. And subsequently, we extended our discussion of transformers towards the end of last week into transformers with some structure within them. If you have different representations at different parts of your elements, how do you combine them in the right way with respect to the structure for the problem? So that's the whole idea of reasoning, right? One common example of structure is that across time. And we saw how transformers and other memory-based methods do that. Another form of structure is hierarchical, where we saw how module networks learn this tree-like structure, respecting the syntax of the question. And we also saw examples of graphical structure. And we talked about graph neural networks in the case where different modalities form some graph. So how do you learn the structure of a graph? So all that falls broadly into reasoning, right? The idea of respecting the structure and how you learn representations that follow the structure. So there's four core challenges in reasoning, four sub-challenges. The first one is that of structure modeling, different types of structure, whether it be single step, temporal across time, hierarchical in the case of a tree and a graph. Today, we're primarily going to be talking about interactive structure, where the structure of the problem changes as you take actions, changes as you make predictions. And for some of you who are familiar, that's essentially the reinforcement learning framework. And finally, we're also going to talk a little bit on Thursday about the case where the structure is not clear, where you might have to discover the structure from data and several ways of doing that. The second big challenge is what intermediate concepts to use. We're always used to using uninterpretable, dense neural network features as intermediate steps. But since a lot of reasoning is about making the reasoning process more explicit, can you use other ways of parameterizing these concepts, whether that be soft attention, hard attention, or even language, right? If you had language telling you at every step, these two things happen to combine to this, which then happens with this. If you have language, then the reasoning process is perfectly interpretable. Right? Nowadays, with language models and multimodal language models, there's an opportunity for exploring language as an intermediate medium for reasoning. The third big sub-challenge is that of inference. We've looked at reasoning as a combination of local information hierarchically into more rich information. How exactly is this combination process done? Right? It can be done in representation space, adding, multiplicative. Again, that's not so interpretable. There are ways that we can integrate logical statements or even causal relations into this combination process. Think about solving a math problem, right? You have this information and this, you can deduce the next one, you can deduce the next step of the proof and so on. Ideally, we also want to have that in our multimodal models. So how do you integrate things like logical statements, causal relationships into the reasoning process? And finally, reasoning doesn't come without external knowledge, right? Typically, you need some knowledge of the problem, either through human knowledge to design your models or through textbooks, other big databases of knowledge, Wikipedia, for example, to inform your reasoning process. So we're also going to talk a little bit about external knowledge on Thursday. All right, so reasoning, four big sub-challenges. We've already saw a glimpse of structure modeling through memory, tree-based, graphical networks. We're going to talk a little bit more about the structure modeling today with interactive structure, where the structure changes over time. And on Thursday, we'll see a glimpse of all of these small but pretty important parts. So how do you discover the structure? How do you have discrete intermediate concepts like language? How do you integrate causal, logical combination functions into the inference? And how do you leverage external common sense knowledge? Any questions about a big picture for reasoning? And we call reasoning is our third big challenge, right? We've had local representations, aligned representations, and alignment. Reasoning is our third big challenge. And after fall break, we'll be talking about generation, transfer between modalities, and finally quantification as the sixth and last challenge. All right. So today on interactive structure, right? So interactive structure is this multi-step structure where every time step, there is some sequence of time steps, and every time step, there is some local information coming in, typically in the form of two modalities. You might learn some representation, you might do some alignment, and you make an action. This action will then influence the next sequence of observations that you see, so the next image that you see or the next instruction that you see in natural language, from which you might learn a new representation, make a new prediction, and then that goes on and on and on. Oh. And that goes on, right? You keep taking actions, making predictions, which then influences the next stage that you see, which then has to influence the next step of actions and so on. And for some of you who are familiar, this is essentially the reinforcement learning setup. And nowadays, there's huge interest in reinforcement learning combined with multimodal, right? Building robots that can navigate the world through this multiple step action. You have to take multiple steps, walk around, using what they see, what they hear, what they feel from their force and touch sensors on robot arms. Some of you might also have seen language models that can navigate the internet, right? You can tell your language model to book you a flight from this city to this city, get your language model to go to Amazon, buy these products that you like in this certain type of color and this price. All of these are multiple decision step processes that have to take into account multiple sensory modalities at every step. Right. So this lecture, we're going to talk about some basics of reinforcement learning. We're going to talk about how reinforcement learning can be extended to multimodal and some applications of that. Right. So some classic examples, right? Some of you might have seen these games where there's this reinforcement learning environment, and your goal is to give some instruction to the agent. For example, go to the green torch, and the agent then has to navigate through the environment, take multiple steps. It might not even see the green torch at first. It might have to move around, follow some maze before it sees the green torch and goes to it. So that's an example of multimodal reinforcement learning. As you can see, there are three big things necessary, right? You need to learn local representations. You need to understand, what is green, how that green word feature aligns and fuses with the occurrences of the green torch in the image. You need to learn aligned representations, such as understanding the entire sentence. What does it mean to go to the green torch? Because you might also get an instruction that says avoid the green torch or avoid the monsters. And finally, you have to do all this in this interactive setup because you have to take actions, which changes the inputs, right? Whenever you take an action, such as moving forward or moving backward, what you see in the visual modality changes. If you turn left, turn right, you might start seeing new things. So how do you essentially combine all this information through reasoning to get the right action? And I put policy here because in reinforcement learning terms, the goal is to learn a policy, which means to output the right action from every state in time so that you can take that right action. So how do we learn a policy? Some basics of RL. I'm probably going to spend about 30 to 35, 40 minutes on this, not too much. To talk about intro to RL, some ways to formalize RL, how to solve RL, and before that, and finally, some applications. So in RL, typically you see this MDP. It's a multiple step process that starts with a set of states. So those are all the states you can visit. For example, all the places you can visit as a robot in that environment of going to the green torch. A set of actions from every state, actions you can take. That may be moving, forward, backward, left, right. In certain games, it might be using tools, building things, and so on. There's some transition function that tells you from a state that I start with and some action that I take, what is the next state that I might end up in? Right? That can be usually deterministic. If I step forward, I'll move forward. Sometimes the environment can also be random. So if I move forward, there's like a 20% chance the wind blows and I move to the left. The reward function, so from a state that I start with, an action that I take, and the next state that I go into, what reward do I get? Right? Do I actually see the green torch and get positive reward, or did I fall into the hole and get negative reward? There's some state that you start at. There's some discount factor because you're going to get multiple rewards, right? There's going to be multiple things that you can do, multiple positive, multiple negative rewards. The discount factor basically is a factor that tells you how much these rewards get discounted over time, right? The reward that I get at this current time step should be the most important. Some reward that I may get into the future, if I take the right actions, should be less important. So that discount factor tells us how much I should discount, 0.9, 0.8, or so on. And horizon is the total length of the multi-step interaction process. And usually the goal is to maximize your whole sequence of rewards, the reward that you might get at this time step, but more importantly, the rewards that you may get into the future, right? That's kind of the main difference between supervised learning and reinforcement learning. In supervised learning, you care about making the right prediction at this time step. You make one prediction, it's correct, you're done. In reinforcement learning, sometimes you might have to take suboptimal steps to get better rewards into the future. And the policy is a distribution. So we usually call it pi. So given a state or any state it might be in, a distribution over actions that you might want to take from that state. Most of the time, the policies are deterministic. So if I were at this state, I should just move forward, go to the green torch 100% of the time. Sometimes the policies can also be random, right? And people can prove that in certain games, random policies are optimal. Like think rock, paper, scissors. The optimal policy is a third every action. So it's random, you just output a distribution over the actions and then you sample based on that distribution. And finally, the goal is always to learn the best policy. So you want to argmax over all possible policies. And the thing that you want to argmax is this reward. Reward being not just the immediate reward, but the long-term cumulative rewards stumbled over time. Okay, pretty simple setup. Some key differences between reinforcement learning and supervised learning. Reinforcement learning involves sequential decision-making across multiple steps. Supervised, typically one step, you're done. And everything in the class we've seen so far was basically in the supervised learning regime. Reinforcement learning, because of this sequential nature, you want to maximize cumulative reward, not just short-term, but also reward all into the future. Supervised learning looks at maximizing immediate reward. In reinforcement learning, a typical hard problem is that of sparse rewards. You might have to take many actions before you see a reward. You might have to navigate for a long time before you see the green torch that you were instructed to visit. So how do you deal with all these sparse rewards of not seeing any reward for a long period of time and still having to learn to take those actions well? So we call it a sparse reward problem. In supervised learning, you typically have dense supervision. For everything that you want to learn in supervised learning, you're determining some reward, you're giving some label so that your model learns it. And finally, in reinforcement learning, sometimes the environment is unknown. You don't observe all the states. You don't know all the places you might be visiting. Again, for example, the green torch, you don't see the green torch at the beginning. You have to move around before you actually see it. In supervised learning, you typically don't deal with that problem. All your modalities, all your data are usually perfectly visible. But there's some intersections, of course. You can solve any reinforcement learning using a supervised learning paradigm. How do you do that? So this is how people used to build self-driving cars, right? And what they used to do back in the day is that they got expert drivers to drive these cars all around Pittsburgh, all around the US. And when these expert drivers drive these cars, they basically record what the expert drivers are doing. Every state that the drivers are in, so everything that the driver sees, the road conditions, the traffic lights, the pedestrians, the other cars on the road, all that is compressed into your state. And then you look at what the expert driver did. Did they move forward? Did they brake? Did they turn left or right? Those are your actions. You give it some reward. And because these are expert trajectories, we're going to assume that these rewards are always good, right? You're always making it there in the shortest period of time without getting into any accidents. And you just keep doing this, right? You just keep observing the trajectories of these expert drivers driving the car. And then you basically get a supervised data set because from every state in this sequence of trajectories, right, you have the expert action. You know what the expert took from that particular time. You can treat it as a data set, mapping your states to your actions. And then you can learn your policy using something like supervised learning, basically. You can take in all the inputs, X, which are your states, and try to predict the action, use cross entropy, mean square error, and optimize. And of course, that may work, but you can very easily see where it fails. Once you go into one suboptimal state, right? Because Your expert drivers only see perfect states. They're never going to drive onto the grass. They're never going to fail to brake in front of another car. So all these states are perfect. But in the real world, you're going to see imperfect states. And your model might also be imperfect, right? So if I kind of make an error and go into some imperfect state, then your model basically doesn't know how to recover. It might get even worse. And that'll be super dangerous if you actually deploy a self-driving car that has only seen perfect states, but once it goes into a small imperfect state, it just spirals out of control and starts hitting pedestrians. Right? So that's kind of one of the issues with applying supervised approaches. People tend to call this imitation learning because you're trying to imitate the expert and you often only see the best expert trajectories. Those are some of the risks of applying directly supervised learning to reinforcement learning. Of course, there are ways to improve this. There are ways to do data augmentation, to force a model to see some of these imperfect states, force the experts to try to recover from the imperfect states. So this is also a ripe area of research. So when you see some papers in vision language navigation or multimodal reinforcement learning, and they say imitation learning, it typically means something like this, where there is some expert trajectory being obtained by humans. For example, humans navigating the robot through the green torch, or humans, showing how to clean up the house. You have these expert trajectories, and then you train the robot to replicate these expert trajectories. All right. If we don't want to stay in the supervised learning regime, you don't want to collect these expert trajectories, so you can think of RL as exploring a tree, essentially. Right? We have this multiple step process from some states, and every state that you kind of explore, you're going to see some actions, some rewards. Right? Some of these rewards might be more, some might be less. And after you go into the next stage from taking those actions, you're going to, again, have a choice of several actions to take, and subsequently more rewards to be seen. Right? So wherever you explore, this tree kind of grows. And this tree can grow very quickly. So typically when we see this tree, it's usually useful to note, first of all, in this case, we're showing the policy pi as blue, right? Pi is a distribution of actions from each state. So this policy is basically saying that from the first state, I'm going to go down. From the second state, I'm going to go down here. And from the third state, I'm going to do whatever. So pi is your policy. And when you think of these trees, it's very useful to assign some values to the nodes of these trees. So we're going to call this V of S. V is your value function. Essentially, this is called a state value function because it takes in a state and it outputs what is the value of that state, how good that state is. And when we measure how good that state is, we call that is not just the immediate reward from that state, it is the expected long-term reward from that state. So it's how much total reward should I expect from following this policy pi from this initial state S. So that's V of S with a subscript pi. So I run it from S1, for example. I can just do this mathematically. So when I run this from S1, I'm going to follow the policy, get a reward of -1. Follow the policy again, get a reward of +100, and so on. So the expected cumulative reward is +99. In this case, we're assuming there's no discount factor. So essentially, this state, how valuable this state is, should be 99. And that's important because if you look at just the first reward that you get, is -1, right? But you got to take into account all the rewards that you might get into the future that may overwrite this -1. So essentially, the value of this state should be 99. The other term that people care about is this Q function. Q function is called an action value function. Action value function because it takes in both the state and the action. So it basically prescribes how valuable actions are from a certain state. And again, this is based on the expected long-term reward, not just immediate reward of taking that action, but what the rewards can be into the future. So again, the expectation under your policy pi, your total reward, assuming that you started from that state and taking that action. So I can again run it from state S1, and let's say what's the value of my action up, following my policy pi. So I go up, I'm going to see +1, and if I keep following my policy, I'm going to see a +2, because it goes down in the next state. So the total, the action value for state S1 with action up is 3. And that's good. Those are state values functions and action value functions for your policy pi. We also care about the optimal, right? The value function for the best possible policy, which is essentially taking an argmax or a max over all policies pi and the state value functions for those policies. essentially saying what is the optimal value of the state, assuming I take the best policy. And again, you see that from S1, you're already taking the best policy, so it's the same as, oh, this should be a star, apologies. From S1, you're already taking the best policy, so the optimal state value function is the same as the state value function for your current policy. And likewise, we also care about the optimal action value function. Assuming I take the best policy, what is the value of those states and actions? In this case, from up, you're not taking the best policy, because once you get +1, you should go up and take the +3, right? So if you max over all policies and you find the best one, the value of the action up from state S1 should be 4. Okay? Yes?
Would you typically pick one approach over, or like, would you typically only pick one of the approaches?
Okay, one of these values to learn?
Yeah.
Great question. They can all be converted to and from each other, right? And it's not surprising because they're essentially encoding the same information. It's just one is in form of the states, one is in form of the actions, one is in form of the current policy, one is in terms of the optimal. So you convert between all of these. If you have the state value function for a current policy pi, you can take a max over all policies to get the optimal state value function. We've seen that. Likewise for the action value functions. You can also convert between action value functions to state value functions, right? Action value functions tells you how good an action is from that state. You take an expectation over the actions with respect to your policy. That gives you a weighted average over all actions, and that gives you how good the state is. And likewise, you can go from this as well. If you have the optimal action, then essentially the value of the state is just taking that best action, seeing how high it is. That gives you the optimal value of the state. Right, so you can learn all of these are the same. Depending on your environment, you might choose one over the other. For example, if your actions are huge and continuous, you might not want to learn your action value functions. If they're small and discrete, it might help to learn those. So essentially, the good thing is that once you've learned these functions, you're essentially learning this tree where you're looking at every state, every action, and you're prescribing the value to the expected long-term reward. And once you have these, you can obtain a best policy, right? A best policy, if you have this, let's just use this optimal action value function, for example. If I'm in a state S and I know the optimal action values, then I can just choose the action that gives me this optimal action value, right? Right. So my policy is just taking the action with 1 minus epsilon if my action A achieves the argmax, achieves the optimal action, and otherwise I might not want to take that action. And note that I wrote epsilon over here. You might think 1 and 0. I'm writing epsilon here mainly because of exploration, right? Even if your policy is great, even if your optimal action values are great, they might not be perfect, right? So this epsilon here is typically meant as a leeway so that you can also explore other actions you might possibly want to take. We're going to see in a second why this can be super important. So the optimal policy can be found if you learn all these value functions. And likewise, if you have this optimal state value function, you can also find the optimal policy. The only issue is that these optimal state value functions only tell you the value of the state. So in order to get the best action from the state, you also have to actually take a couple of actions, right? That gives you some immediate reward from taking those actions. And then once you go into the next stage, you see how valuable that the state that led you from the action was. And you have to add both of those up, right? We call this one step look ahead. So there's one big paradigm. One big paradigm is kind of recursively computing these state and action value functions. We saw how to do it in a simple example over here. I'll get into a little bit more detail how to solve it exactly, but at least you have an intuition that you can solve it essentially recursively, right? You search through and just compute. You can be done using math, basically. And once you compute all these state and action value functions, telling you how good states and actions are, you can use that to tell you what is the best policy by just taking the actions from the states that are optimal. The other big paradigm is called policy-based methods. In policy-based methods, we're not going to try to learn the values of states and actions. So we're not going to learn these Q's and V's. Instead, we're just going to directly learn a policy. Right? Policies are just functions, right? Functions that take in a state S and outputs a distribution over actions. let's just say I'm going to use, a function approximator with some parameters data that takes in S and outputs a distribution over actions. So I'm just going to directly learn the policy without learning the values of the states and actions. And this can be helpful sometimes as well. Sometimes your policies can be simpler than your Qs and Vs. Your Markov decision process might be very complicated. There might be many states and actions. So learning Q and V can be very difficult, but Pi can be easier, right? One example is just picking something up. All you have to do is learn a sequence of actions to pick something up, a robot picking something up. That can be what's learned in the policy. Whereas if you try to prescribe all the states and actions, you might have to look at all the joints in your first finger with all the angles, all the joints in the second finger and all the angles. The number of states and actions might be very large. And sometimes Pi can be easier. So your Q and V are very high dimensional, but a policy is just, closing or opening your hand. The other issue with the value-based methods and why people might prefer policy-based methods is that for both V and Q, there is some difficult optimization you might have to do, right? Over here, we saw that there is an argmax over A. So the A is large, continuous. You might not be able to do that argmax very efficiently. And even if you did from the V space, you have to do argmax over A as well, right? So sometimes you might prefer to directly learn the policy. How exactly we'll do it? We'll spend about maybe 10-15 minutes talking about it later. But essentially, just as a very high-level overview, two general types of methods, right? When you read the literature, some people would say policy-based methods, policy gradients. That's one. Some other people might say assigning states, action values, that's value-based methods. But value-based methods, they generally tend to be more sample efficient because you're respecting the structure of the problem. You're taking into account the fact that you do have an MDP that has this recursive structure where values of states are dependent on the values of states that can be achieved by actions from that state. You're expecting this symmetric recursive structure, so it can be more sample efficient. Policy-based, it doesn't really respect the structure of the problem. It doesn't even know that it's an MDP. It doesn't even know that it's doing reinforcement learning. So it can be less sample efficient, right? Think of the classic domain knowledge, hand engineering some features, whereas everything purely data-driven, right? The value-based ones is usually more sample efficient than the policy-based ones. Value-based ones also tend to be easier to add some domain knowledge. If you know how good certain states and actions are going to be a priori, you can inject that into your model. One classic example is, I know some of you know, like the first iteration of AlphaGo, right? And the first iteration of all those like chess playing, Go playing robots or AI agents, most of them were value-based, right? So they had state configurations that were good, or they knew that they were good by chess experts, and they assigned high value to reaching those states. And therefore, when you learn a policy, the policy should prefer reaching those states eventually because those are known to be good by humans. Similarly, for AlphaGo, they had these functions that had convolutional networks that took in the state of the game and estimated how good the values of those states were. And afterwards, they basically could obtain the policy by search. Right? That's what they call Monte Carlo tree search. Right? Once you know which states were good, you can essentially approximately search for the good states. Right? So it's easier to add human knowledge. Policy-based is a bit harder. Policy-based are purely data-driven. You're just learning a function approximator from states to actions. Less research in adding human knowledge. The issue with value-based then is that it is more complex, right? We're going to see a little bit, there are some equations, a little bit ugly equations, because you're essentially going to this MDP and you're trying to compute recursively the values of the states and actions. There's going to be a bit more math and complex algorithm involved. Policy-based is going to be simpler. It almost very closely recovers supervised learning with function approximation. Value-based has some other issues I've also mentioned. You can't really handle the continuous argmax. It can be harder to understand. Sometimes the values are very complex. When there's lots of states and actions, you probably wouldn't want to use value-based. And policy-based directly learns the policy. So it can be more interpretable, right? If I give you all the states and action value functions as a list of numbers, it might be hard to understand. If I just tell you the robot is trying to learn to close the hand, open the hand, move further away, from the policy perspective, it can be more easy to understand. Right? Any quick questions about these two general paradigms of reinforcement learning? Most of the things here is to help you read the literature, help you design your own methods. Essentially, you just want to know at a high level what these two methods are kind of doing. And of course, the trade-offs. Cool. So I'm going to try to cover the essentials of policy-based RL in about 15 minutes. I think most of you should already have some intuition about this based on the tree that we showed, where you can recursively compute the values of states and actions by traversing the tree, right? But to make this more formal, essentially you can see these trees as this, where the white circles are states, the black dots are actions. So when say you can take a couple of actions that leads you to some next states, and the goal is to compute the optimal state value function for these states and also the next states that can be achieved by taking those actions. And I kept mentioning that there is some recursive definition, right? And this recursive definition shouldn't be very surprising. You can essentially write the optimum value of that state as a max over the best optimal action value from that state. And once you go into those actions, you can then write it as the reward, the immediate reward of taking that action, plus when you go into the next state, the optimal state value function in that next state. So very easy, right? The optimal value function of yourself is the action that you take, the immediate reward that you get. When you go into the next state, the optimal value function of that next state. So it can be defined recursively. And this is just writing the expectation as a summation, right? It depends on a couple of important things. You have to take the argmax over the actions. You have to look over what next state you might go into. The key is the transition function that tells you the distribution of next states I can go into, the immediate reward that I get from that action, and then for those next states, the optimal state value functions. And likewise, you can do the same thing for your action value functions. It's not very surprising. The optimal value function from this particular action is the value of the next state that you go into from that action, and then what possible actions you can take, those rewards plus the action value functions from those next states. And the good thing is that once you can write out this recursive definition, you can basically solve it. If you know all the states, you know all the actions, you know all the transition probabilities, this essentially becomes something like a linear program you can solve. We kind of did it by hand in the tree case, but essentially you can just compute and solve these equations. In a case where S and A are larger, you can solve using iterative methods. Essentially, there is some equation that you want to balance. The left side and the right side should be equal with each other. So I can compute something on the left side and set it to the right side and repeat. So that's kind of the first set of methods, right? Think of it as value iteration. Essentially, you're starting from some state that you begin with. You're going to traverse the tree, right? When you traverse the tree, you're going to see actions, get rewards, and go to the next states. And you're just going to keep a list of V of S for all S. That's basically a list or a table. And whenever you visit some state, you're going to update the entry in your V of S. You're going to update the entry by the rewards that you get, and also the V of S looked up from the states neighboring it. And after you do this enough, after you visited all the states, you can essentially get the accurate list of the value functions from all states. Right. And this kind of is a guarantee that it converges if your states and actions are small and discrete. This is guaranteed to converge. Likewise, you can do the same thing for Q, right? I won't get into the details, but again, in this case, you don't have just a list of V of S, you have a table of all the states and all the actions. And whenever you're going through your tree, you're updating the values within this matrix. Right, so these are basically what we call exact methods, because if the number of states and actions are small, you can compute all of this exactly basically just using the equation. The bad thing about this is that, well, there's a couple of bad things. The first bad thing is that it requires this transition matrix. So you basically got to know from every state and action, what is the next state that you go into. And usually that's a very big assumption. You can't really do it for like self-driving cars. You can't do it for robotics, many different things. And a very easy trick is to just rewrite this exact summation over next possible states as an expectation over next possible states, and essentially approximating the expectation with empirical samples. right? So you may not know the entire distribution of next states and the exact probabilities, but you've played around in the environment enough to know that this state happens 5 times. This next state happens 2 times. I'm going to replace the expectation with this empirical probabilities. Still a pretty similar idea. You're doing the same thing for every state action that you're going. You're going to take, in this case, we're using the action value function. So you're going to read into that entry in the matrix. You're going to respect that equation, that recursive equation where your QSA for your state is a function of the current action's reward and the QSA of the next state and the next actions, right? Essentially respecting this recursive structure, you're expecting it by knowing that this left-hand side should be equal to the right-hand side. There's 2 terms that must be equal in that recursive definition. So take the left and right-hand side, subtract each other, treat it as a difference, and try to minimize that difference to 0. Right? And you know that 2 sides must be equal, so take the difference and minimize that to 0. So essentially, you're updating your entries in the matrix until eventually you converge. Eventually, you get the SA matrix where all pairs in the SA matrix respect the equality. Right. So that's about tabular Q learning. Nothing really complex as well. You start from a state, you initialize your matrix, you start from a state, and always just keep trying to minimize the left-hand side and right-hand side to be exactly equal. Right. This is essentially the optimality equation that we derived from the recursive structure. So once you get into these approximate methods, because we all came here because we didn't know the exact transition matrices, right? We wanted to sample it, essentially take a bunch of actions and see what the distribution of next states might be, which one gives you the highest rewards. So that's why over here, the epsilon thing becomes important, right? We call that, how do I choose the action? Should I choose the action based on my current policy, or should I randomly choose my action? Randomly choosing an action can be very useful because you can then start exploring the environment, right? The policy that you started with may be suboptimal. So once you start from a bad policy and you keep exploiting that bad policy, it's going to get worse and worse. You need to leave some room to explore the environment, to see other better states that your policy may not have seen yet, and see high rewards that your policy may not have been trained for yet. So exploration is very important, right? So typically always in reinforcement learning, when you kind of traverse the tree, so-called, or traverse the environment, so-called, you want to be a mix of random actions. Usually you start random actions in the beginning. So you see a large amount of states and you see the good rewards. And then you're going to start learning your policy, right? You're going to start learning your V's and your Q's. That tells you which states are good and bad. You want to then follow these good and bad states, good states. But you also don't want to always follow these good states. You want to leave some room, with probability epsilon, you want to leave some room for you to kind of keep exploring and make sure that you're not stuck in some local optima. And if there are better states, you might be able to visit. All right. So that gets you tabular Q learning, right? You're still keeping this matrix of states and actions and the Q functions. But now you're starting to explore. You're trying to get an action based on a combination of exploration. So random actions, taking random actions, and also following the current best QSAs that you've been learning. And you want to balance this, right? You start with more exploration, more random policies, and eventually you go to policies that more closely follow the states and actions with the high values, the high QSAs. All right, and final issue, right? This still depends on the matrix of states and actions. It doesn't really work if your states are images, actions are large and continuous. So finally, deep Q learning, right? Deep Q learning extends the previous tabular Q learning to deep neural networks, where the states and actions, the Q functions of your states and actions are not a table, but rather parameterized by a neural network. Right? So these neural networks take in, it can be 2 ways. One, the easier way is you take in the state S and you output the QSA for all the actions, right? So I take in the image and I output the QSAs for all the actions and how valuable they are from that starting image. This works better if your actions are discrete, if you can only move up, down, left, right, for example, if you're in a maze. If your actions are continuous, then it can also help to take in both states and actions. Take in the image, take in some continuous vector that represents your robot arm. And together, outputs QSA, telling you how valuable, from that state and that configuration of your action is. And because we're using deep neural networks with some weights W, you're essentially approximating this table of QSA with every entry independently with a neural network that learns QSA for every state of action, for every state in action. And of course, it generalizes to high-dimensional states, continuous states, and also generalizes to unseen states. Right? You've seen a state with this image, even if you change the background, you change the lighting, you move it a little bit left and right, it's still going to be able to output the right value of that state and output the right values of actions from that state. But the idea is the same, right? The idea is the same as what you've seen previously. It's just that we replace the table of QSAs to the neural network. So the optimal values, the Q functions that the neural network output should still respect that equation, that recursive definition, where the QSAs of your current state is a function of the QSAs of the states that you visit next. You should still respect this equality equation. How do you respect it? Again, there's a left-hand side equal to the right-hand side. It should be equal at optimality. So take the difference, left minus right-hand side, take the difference squared, treat that as an error, right? You want to minimize the error to 0. And if you minimize the error to 0, you've succeeded in learning the QSAs that respect the recursive definition. Okay, so that's kind of the objective function. The left minus right-hand side. So QSA for the current states of actions should be equal to the immediate reward plus the QSAs for the next actions that you end up visiting. That should be 0. There are some subtle tricks that people have discovered to get it to work better. So it still converges, but can be 2 main issues. One main issue is that of correlation between samples. When you see these things, because you're essentially training this on state action pairs that you obtain from the environment, right? Every state or state action you're obtaining from the environment, you're going to put it into a neural network and learn QSAs. So you start exploring from state 0, action 0, state 1, action 1. So you take S0, S1, you put it into the model, then you take S1, A1 into the model, S2, A2 into the model. You're essentially getting samples that are very correlated. Right? The equivalent is kind of like you're training on ImageNet and you're just giving a bunch of cats, like 100 cats in a batch. And you give it 100 dogs in a batch. You give it 100 humans in a batch, 100 computers in a batch. Right? Correlation is typically not good because it forces your model to like overfit to one class. And then in the first batch, like the class for cats, and then it starts overfitting to the batch, the class for dogs in the second batch, and they overfit to the class of humans for the third batch. That's typically not good. Right? We want these samples to ideally be IID. So one thing you can do very easily is to take all the S1, S2, S3, S4 that you obtain from the same trajectory, get a lot of them, like 100,000 of them, and just randomly shuffle it. And shuffling it essentially allows you to remove the correlation from your samples so that now you're actually seeing states that are IID with respect to each other. The other big issue is that your targets are not stationary, right? Because essentially this model is kind of weird, right? It takes in states and it's going to output QSA, right? The values of those states or the states and actions. But these QSAs are changing across time. So it's kind of like when you're training on ImageNet, but you have images, and sometimes the label is cat, sometimes the label is dog, sometimes the label is horse. The label for the same image keeps changing. So that's the issue of non-stationary targets, also an issue. And one thing people do is to kind of keep 2 copies of these models, right? One copy that is kind of frozen with frozen parameters, maybe 100 epochs in the past, and another one that's getting updated. So on the 2 sides of the equation, one is using the latest model with parameters W, and one is using the old version of the model from 100 epochs ago. We call that W minus, right? So at least you keep one side of the equality frozen. The targets are fixed, and you're only training the current model to match those targets. And maybe after like 1,000 epochs, then you initialize the old model with the newest weights. Right? So we call this like fixed Q targets. Also found to be very important. Yeah, so that was kind of the value-based learning in about 10, 15 minutes. We looked at the tabular case, Q learning, where you're just learning QSA as a matrix. You just want to learn this matrix where you respect the equality, right? The values of your states is a function of the value of states that you can visit from those actions. And then we kind of saw the extension to deep learning, where instead of learning this entire matrix, you parameterize by a neural network, right? So when you read papers, a lot of people, when they say they use this deep Q learning for like multimodal navigation.
What is it?
Right, so the issue here is that there's this issue of non-stationary targets, right? Essentially, you're using a model S to output some target. Usually that target should be fixed, right? The label is just kept. But here the output is QSA, and the objective function is essentially this Bellman equation that tells you the fact that this QSA should be a function of QSA from your next states, right? That's the objective function. So in some sense, you don't have a fixed target. You have targets that are changing over time, right? Whenever you give a new data point to the model and you take a gradient step, your QSA for your current state changes, and your QSA for your other neighboring states might also change, right? So when you're trying to optimize an objective where both of these QSAs are changing a little bit over time, it's going to be hard for the model to converge. What this frozen thing does is that I'm going to at least freeze one side of the equality, right? I'm going to fix, in this case, I'm going to fix the QSAs of the neighboring states, and that's going to be fixed. I'm just going to train a QSA of my current state. So then it becomes closer to supervised learning, where the target is to reach the QSA of the neighboring states, so the weighted average of QSA for neighboring states, and I'm going to train the QSA of my state to reach that for maybe like 10 epochs. And after that, I'm going to have to eventually update the QSAs of my neighboring states, right? So I'm going to, after 10 epochs or some number, I'm going to unfreeze and update it with the latest. Great. Okay, so that was more value-based, where you're learning the state action value functions. Policy-based, as you recall, is not learning these state and action value functions and just directly learning the policy. So here's a very easy example. So let's say I want to train this AI to play this Pong game, right? Well, one person is like the AI, and the left one is the one that I'm trying to train. So just directly learning a policy can be seen as learning a neural network, with inputs being the frame for the game, the pixels in a game. So that's an image. And you can define some parameters and output your actions, right? In this case, the action is just two actions, right? You either move up or down. So I can just have one neuron that tells me what probability I move up. Down is just 1 minus that. So the network, the reward is that you see in this game, the simulator, the reward that it spits out is 1 plus 1 if you manage to score a point against the other opponent, and minus 1 if the opponent scores a point against you. So the next question is, how do you learn these parameters? So think about what we do in supervised learning, right? In supervised learning, what we have is, and I'm mentioning supervised learning because these policy-based learning is actually quite similar to supervised learning with some subtle differences. But essentially in supervised learning, you have the states, x1, x2, x3, and you know what are the best actions to take from those states, right? At this state, you have to move up, this state you should move down, and so on. And how you would train this model is you will maximize, in this case, the log likelihood, right? You will try to maximize the probabilities of the actions, the right actions that you're given from the input states. Of course, now you don't have labels. You don't know from every state, should I go up or down? So what can I do? So let's just start randomly, or you can start with your current policy, do the exploration as we talked about. So we initialize the model, start randomly, okay? There's some sequence of actions, down, up, that you win. So you get a +1. Let's say you're lucky. And you keep doing this. There's some sequences where you win, some sequences where you lose, some where you win. And what I'm going to do is just, I don't know, the model doesn't know what exactly we did in this sequence of actions where you won in the end, but obviously it should be good, right? You won. And you're not really sure which exact action that you did in the other two where you lost eventually, but you know that the whole sequence was good. You eventually, it was bad. You eventually lost. So for all the trajectories where you won, I'm just going to, yes.
So the opponent is also doing something.
Right. So your opponent is a simulator. The opponent is a simulator, right? So the only thing that you can control is your actions, whether you're moving up and down. So you can move up and down over a sequence of actions, and then that's going to score a point against the opponent based on the opponent's action.
Yeah, right. Classes the simulation to make every time in every round.
Oh yeah, the simulation is the same. So this is not like multi-agent where you're training you and someone else is training them. That's kind of like the extension, but in this case, the opponent just has a policy and that's kind of fixed.
So it always fetches the same set of actions.
Their policy may be randomized, but it doesn't matter, right? It is basically just the environment they're interacting with. They're always going to take some actions. It doesn't matter if they just always stay there or like they keep moving up or down. The only thing is that you are training your policy against them. So they're fixed. You're training your policy against them. Right? They're not, their parameters are not getting updated. In fact, you don't even have access to their parameters. It's almost like a black box, right? The only thing you can interface is that you know what the current state is, you take an action, and the environment spits you out the next state and the next reward. Those are the only things that you see. Did you have a question?
Yeah. So if I were to do this in practice, the state would have to capture some sort of temporal information, right? Otherwise, I wouldn't know where the direction the ball is going.
Oh yeah, good question. Yeah. People do. So you look at the Atari games, like this is Pong game, this is like breakout game. Usually their states is going to be like some LSTM with memory or some model with memory, or you can concatenate the last 4 states and treat. So this is not every action, right? This is going to be a sequence of steps, and the feedback only comes if you score a point against the opponent or they score a point against you. Right? That's what makes it challenging, right? Because you have to take like 10, 20 steps before you might be able to score a point against them. So. Yeah, great questions. So the sequence of steps that were good, there was a sequence of steps that were bad. You don't exactly know because you don't have to report at every step. So you don't exactly know which specific action led to the final outcome, but you know this whole trajectory led to this win or lose outcome, right? So I'm just going to pretend for the trajectory where you eventually won, that all the actions were good. It's a pretty naive assumption, but let's just stick with that for now. Let's assume that all the actions in that were good. So I want to maximize the log probability of those actions. Right? So in green, maximize the log P of y given x, or P of a given x. For the trajectories that you lost, again, I don't know which of them were exactly the one that caused me to lose. I'm going to do something naive. I'm going to assume that all of those actions are bad. So I'm going to minimize the log probability of those actions, or maximize the -1 times it. And finally, I'm going to discount. I'm just going to make this simple assumption where the actions that were taken closer to the outcome were more important than the actions taken early on, right? You shouldn't expect an action like 100 steps, 1,000 steps into the past to be that important. So I'm going to add this discount factor. The same discount factor as you saw in the MVP. And that gives you a pretty simple algorithm. Initialize your policy at random. So initialize your neural network at random. At the start, it takes in states. It's just going to output random actions, right? Because your policy is random. It's going to take random actions. And you're going to repeat collecting a bunch of rollouts using a current policy, perhaps with epsilon greedy exploration. Whenever you see states in action, some of them are going to be good. Some sequences are going to be bad. For the ones that are good, I'm going to maximize the log probabilities with a discount factor. For a sequence of actions that led me to a negative board, I'm going to minimize those log probabilities, again, with a discount factor, right? So you can write overall as, just always maximizing the log P of y given x for every action you see in your states with some factor A, where this A is a function of both the reward, +1, -1, and your discount factor, right? Your gamma to the power of number of steps the action was previously from the reward. So this algorithm seems very simple. It doesn't require knowing transition probabilities, how your states and actions go to next states. We saw that could be an issue. It doesn't require estimating your Q's and V's, your state and action value functions. We saw that could also be an issue, but rather it just directly estimates your policy. It just directly trains its policy network based on this objective. And it can actually work pretty well. After a while, you can start learning to play pretty well. So just for a little bit of derivation, just kind of 5 minutes. Why does it work? This actually is proved to work in certain settings. Essentially, this equation is called policy gradients, and it's actually a very useful equation. It's going to be used here. We're going to see it next week as well when we do some optimization over discrete structures. You're going to see it in actually quite a lot of places. So when you hear policy gradients or like reinforced, they call it reinforced in all capital letters in some papers, this is what they're referring to, right? So I'm just going to generally define a class of policies, pi, with some parameters theta. And for each of these policies, we're going to define the value, right? The value should be the expected long-term reward from following that policy, right? Not just the current step, but discounted rewards all the way into the future. And you can essentially write this down in terms of trajectories because you saw we are collecting trajectories. Some simple identities. The probability of a trajectory is essentially, for every SA, the probability that your policy took the action from that state times the probability that you transition to the next state, right? That's the definition of what a probability of a trajectory is. The reward of a trajectory is just the sum of accumulated rewards from your 0 step all the way to the end with a discount factor. And essentially, you can write how good a policy is as an expectation under your trajectories, the reward of the trajectories following that policy, right? Nothing complicated, right? You see your policy tells you SA. How good a policy is the probabilities of those SAs and the reward of those SA trajectories. So that's the value of a policy. If you want to find the optimum policy, just do argmax, right? Argmax, simple way of doing argmax is to take gradients and update parameters with respect to gradients. So gradient ascent on policy parameters. So how do you compute the gradient? So you know that the expected, how good the policy is just the expectation of trajectory from that policy, reward of the policy, a reward of trajectory. So that's its integral. Integral over trajectories, reward times the probability. Take the gradient with respect to theta, which is your policy. So the reward is just some scalar values. So that goes inside. But this is the hard part. The hard part is how do you compute a gradient with respect to how likely the trajectory happened. And if you recall, how likely the trajectory happened is this very complex multiplication, right? You have essentially at every step, the probability of you taking that action and also the transition probability. That's actually very complex. But you can use a cool trick, which is that the gradient of P is equal to multiplying by P at the top and the bottom, right? P of tau at the top, P of tau at the bottom. And this second term, so the gradient of something with respect to the same thing is just gradient of log, right? Gradient of log of that term. So you can then plug this back into the equation. So this gradient of P is replaced by P times the gradient of log of P. And then you get back an expectation, right? You have integral over tau, P of tau, d tau. That gets back an expectation over tau. And what's inside the expectation is the reward of that trajectory and the gradient of the log of the probabilities. And this log is going to come in very handy, right? If you look at the log, the original term was this very complex multiplication. The log goes in and the multiplication becomes summation, right? So you have log of the transition probabilities plus the log of the individual action probabilities according to your policy. And when you take a gradient of the log, when you take gradient of the log, the gradient goes inside a summation. The transition probabilities are constants that don't depend on the parameters you're taking gradient with respect to. So that goes away. The only thing you're left is a summation of the gradient of the log probabilities that your actions were being taken under that policy, right? And finally, you plug it in. The gradient, the whole gradient you want to take is equal to an expectation over the trajectories. And we saw that becomes a summation over the reward of the trajectories times the log probabilities of the actions that you took in those trajectories, right? It doesn't depend on the transition probabilities. That's good. It also doesn't really depend on, it kind of got rid of the nasty multiplication, and that's also good, right? And this time has a very simple explanation, which is that if the rewards are high, right, these are gradient, this is the gradient. If the reward is high, I'm going to just push up the log probabilities of the actions that gave me these high rewards. And if the rewards are low, I'm going to push down the gradients of the log probabilities of the actions in those trajectories. All right, and that exactly recovers what we saw. Exactly recovers what we got a little bit intuitively which is that I'm going to maximize the log probabilities with respect to A, where A formerly was the reward of your trajectories with the discount factor. That over here, it's basically just saying that, okay, so I have a long sequence of actions that eventually led, like maybe 10 actions eventually led me to observe a +1 reward. Right? I'm more likely to assume that the nearest actions contributed more to the +1, and the older actions didn't contribute that much to the +1 reward. So even though I don't know exactly which action contributed, I'm just going to roughly estimate that the immediate action was +1, action previously was +0.9, the action even earlier was +0.81. So there's a general reinforcement method for doing policy-based learning. You're again going to start from a random policy with random weights. At first, it's going to be terrible. It's going to take a bunch of random actions from your states. Some of these trajectories are going to be good. Some are going to be bad. And for the good ones, I'm just going to uniformly increase the log probabilities of the actions with the reward of that trajectory, which again takes into account the reward G and also the discount factor. And for the trajectories that were bad, I'm again going to maximize it, but now your rewards are going to be negative. And of course, how do you actually obtain trajectories? Again, epsilon greedy with exploration, right? In the beginning, explore more. Your policies are terrible, just explore, hope that you're going to find some good trajectories. Eventually, as your policy gets better, you can follow your policy a bit more, but always leave room for some epsilon probability where you explore, where you take a random action. So this method seems a bit simplistic, which is that, if you have, so one issue here, why it's simplistic is that if you have an environment where you just always get positive rewards, right? Some environments are positive, negative, but some you always get positive, or some you always get negative, that's not good. In that case, you would just always increase the probabilities of your actions without kind of making sure you don't take some actions. So a simple way of doing this is do variance reduction with a baseline. Essentially, you want a baseline function that tells you on average how good the rewards are, right? So if an environment is always positive, your baseline will just be an average positive number. And then you can better estimate whether the current action is more than a baseline and positive or less than a baseline and actually negative. So there's some tricks of doing this where you kind of have the same equation, but now your rewards are minus some baseline. And some cool thing is that you can combine these policy-based methods with the previous value-based methods, because what is a good baseline? A very good baseline is actually, the optimal value of the state or the optimal value of the action, right? That tells you in expectation how good that state should be. And when you do policy-based methods, you should just be better. You should give higher likelihood to actions if it's higher than this value function that you estimated. And likewise, you should push down the actions if it's lower than the action values you estimated. So in fact, you can still use a policy gradient function, but one way of defining the rewards is the action value function. So what's the optimal value of taking that action from the state minus the baseline value for the state, the general optimal value for the state. And then you go into all these types of actor-critic methods where you combine both, right? Where you can learn the Q and the V's. That tells you how good your actions are as compared to the baseline for the state. So Q minus V. And once you have Q minus V, you can use that to learn the policy using a policy gradient equation. Now we are still doing the log probabilities, maximizing or minimizing. It's just you're not using raw rewards, but using your Q minus V function. So a lot of things nowadays actually use actor-critic methods or multimodal extensions of actor-critic methods based on this intuition. Okay, that mostly wrapped up the details of reinforcement learning. Any questions? A lot of the equations, there are whole courses on RL, so I'm not going to cover everything in detail. But if it's interest, definitely do check out more, okay? So yeah, so how do we need to use the multimodal? This is the survey paper I like a lot, a survey of reinforcement learning in form of natural language. The survey paper in 2019, it kind of surveys the first half of reinforcement learning. Like some of you probably know that deep RL, deep reinforcement learning, like really boomed in like 2016, 2017. Lots of work in kind of like the technical aspects, but also a lot of work in deep RL plus language. So this kind of surveys the first half. We're going to put up some papers on Piazza, maybe this week, maybe next week, that kind of surveys the second half, because nowadays there's kind of a new resurgence in reinforcement learning enabled by language models, right? We've seen language models for robotics, language models for navigation, language models for even like web navigation and so on. It's kind of a new era of language more helping reinforcement learning than its previous era. Okay. For its previous era, there's still some very cool works. Most of the data sets and environments are actually still from this mentioned in the survey paper. There's essentially two general paradigms. The first paradigm, the one that's easier to explain, is task dependent, where language is kind of important for the task. So you have language assisted because there's some environments where language tells you what happens in the environment. For example, the fact that keys are generally used to open doors. And there's also environments that are language conditional, where language is inherently part of the environment. Language specifies the task which you want the agent to complete, like go down the ladder, walk right, open a door, and so on. There are other ways which are more task independent, where language in general, independent of the task, provides some general domain knowledge, right? The fact that keys are used to open doors, you got to make sure the right key is there, and so on. So in detail, the first type is more language conditional, where language specifies a task. We've already seen this example where you want to give an instruction, go to the green torch, and get the agent to follow this instruction. And a very important thing here is both fusion and alignment, right? You got to fuse, learn representations that fuse the language with the image. And also alignment, you got to figure out that green actually specifies this color and torch actually specifies this shape. But only with alignment can you then generalize to unseen shapes and unseen objects, right? You might go to the green object during training, but go to the green torch during testing. So what these folks did was to design a model where language and image were fused at the state level, right? So the state contains both image and text. They learned this gated attention, we call it gated attention from multimodal fusion, week 2, that learns how to modulate my image with respect to language instruction, right? So essentially, this should highlight parts of the image that were green and has a torch inside of it. And that can then be used to learning your policy. Right, and it shows some cool examples where you can start training on easy ones, where everything is fully visible. So when it's fully visible, the fusion is easy, right? You have this gated attention that is able to learn which parts of the image specifies a green torch, right? That's easy. In a medium case, you have some occlusions, but it's still relatively easy. You can still highlight the parts of the image where there has a green torch. And when you go hard, it's harder because you don't see the torch to begin with, right? So you can't really do fusion at the beginning. You can only do fusion at the end once you've navigated around and you're in a state action or image text pair where you see the green torch referenced by the language. Right, so that's why they have this like gated attention where the fusion in some sense dynamically changes with respect to what image you currently see and what instruction is provided. And it showed that it learns some grounded representations. It learns separate feature activations for colors, blue, red, yellow, green, and learns separate feature representations for your pillars, pillar, armor, torch, skull key, and different objects. So if you train on a couple of them, you can then generalize the new combinations during evaluation. Okay, so that was instruction following. You can extend instruction following to question answering. Again, embodied version of question answering because you don't see the full image right off the front. You have this embodied environment where you have to both navigate before you can kind of see the object of interest, right? Over here, what is the color of the car? You don't see it yet. You have to navigate until you see the orange car. It's the same issue, fusion and alignment, but interactively, right? You're not going to be able to fuse or align something that you can see. Somehow the interaction, the reasoning has to be trained end to end to inform you when you can do fusion and alignment. Yes?
In the last task, the hard setting,
right, so in this case, this is the architecture, right? They have image and text representation. They're both coming in as the states. Think of that as cumulative as the states. They're doing the fusion and alignment at the state representation level. And once you have that state, you can then put it into your reinforcement learning, your Q learning, active critic methods that take in the states and output the actions. But everything is trained end to end, right? Everything is trained end to end, and that's kind of important because you can't always do fusion without knowing what actions you might be taking. And likewise, you can't really take actions without knowing how the multimodal features might be changing or what the multimodal features are. Right? So everything was trained end to end in this case. And I think they found that this gated attention was also relatively important because you shouldn't always kind of concatenate or do fusion all the time. Because sometimes you don't see the alignment between the image and the text because you don't see the object in the image.
And
Yes.
this can be done for both policy-based and value-based, I think.
Yeah, so in fact, they use, I think, active critic methods, which is the one that combines both, right? Where you learn, it's a policy-based method, but the baseline, the reward is like the Q minus V obtained from value-based. Okay, so embodied QA. A lot of works in embodied QA have some human demonstrations, have some ground truth trajectories. So when people say that they do like imitation learning or they have ground truth trajectories, you want to also remember the first kind of first algorithm we talked about, right, at the beginning of class, where you obtain expert trajectories and use that as a supervised learning signal. And they probably fine-tune using reinforcement learning. All right, a few other examples. This goes into the realm of more language assisted, where language is not explicitly part of the task, but it is part of the environment that kind of tells you additional information. Right over here, you can use language to kind of specify your goal, specify what you want in the end, build an L-like shape on red blocks. Over here, this is a famous environment that is very difficult. It's called Montezuma's Revenge. It's very famously difficult for having sparse rewards. You have to take like 1,000 actions before you actually obtain some reward at the end. And these 1,000 actions involve like avoiding enemies, collecting keys, opening doors, climbing up ladders, and so on. But the environment only gives you one reward at the end. So one thing people have been doing is called reward shaping, where you just manually add external rewards into the environment, right? Because in general, people know that kind of jumping over enemies is good, right? So add that as an external assisted natural language instruction, right? Generally, people know that collecting keys is good. Using keys, keeping them until the doors, you see the door, using a key to open a door is something good. So use that instruction as an additional reward so that you're not just limited by the sparse rewards that the environment gives you. Language can also be used to instruct preferences to determine the reward. For example, if you're training a web agent to help you book flights, then the instruction can be book flight, but once it starts navigating and it kind of asks you, do you want the JetBlue flight or the Delta flight? You might say, I prefer JetBlue, even if it's expensive, right? So that's external language helping you guide what rewards your model should take in. As here's that example from Montezuma's Revenge in more detail. How exactly they got the language was from Amazon mTurf. So they asked annotators to play the game and describe kind of the sub-steps that these annotators were taking. So I believe they ran 2 experiments, because when annotators play the game, they can also record the exact state actions of the annotators playing the game. They also asked annotators to get more high-level instructions, right? Like jump over the skull or collect the key, open a door. And there's probably pros and cons to both, right? Collecting a state action is more low-level signal. You can use that to train your model more directly. But collecting these high-level plans is more generalizable, right? Because now you're learning general features that can then be transferred to other environments, other levels of the game. So both can be good. Okay, several other examples. Reading instruction manuals. Oh, yes.
I'm just curious why not done.
Oh, because it's expensive, right? You gotta go to mTurk and it's not really generalizable. But the cool thing is I'll show you a little bit, and there'll be some papers where nowadays you can replace this mTurk step with like language models. You can take GPT, you can ask how to play Montezuma's Revenge, and it can actually decompose some steps, which is why there's this recent resurgence of using language-based instructions to inform robotics, reinforcement learning, and so on. Yeah. Yeah, basically what most of these, when we say reward shaping, is usually that the environment only gives you like 1,000 steps and a +1 reward, and that's not very useful. But if you complete these sub-steps well, you basically say, okay, you complete sub-step in 10 steps, plus 100 reward. You fail this sub-step after 20 steps, you get negative 50 reward. And there's quite a lot of engineering going on, right? Because you gotta know what the sub-steps are, you gotta probably train a model to determine whether you execute the sub-steps correctly. And then you're basically writing some code. It's like a bit hard coded that tells you here's like +100 if this happens, -50 if this happens. Okay. But I mean, every paper will do it a bit differently. So another example is instruction manuals. This is a very famous game, Civilization. It's a very difficult game. You're basically trying to build your own civilization, starting from like collecting natural resources, building cities, building transportation, and so on, trading with other cities. So if you get an RL agent to play this from scratch, it's going to be almost impossible, right? You get humans to play it from scratch is also almost impossible. So even humans will read instruction manuals first, where you have these excerpts, right? The natural resources available are produce food and goods, blah, blah, blah. So you can essentially train a model to choose relevant sentences. So you can think of an attention-like model that takes into account both the instruction manuals and the entities that you see in the environment, and that will help you pick up which parts of the instruction manuals are important. Same ideas from fusion alignment apply here. What these folks also did was they categorized the instruction manuals into things that are describing the actions, things that are describing the states, or things that are more general background gameplay, right? Action descriptions would be, okay, here's how you farm, here's how you trade, here's how you do this. State descriptions are like, oh, here's how you here's how you gauge how much natural resources you have, here's how you gauge where to build a city, and so on. Right, and then they essentially build a model that first picked up the relevant sentences, identify it into state and action descriptions, and again, use this for the rewards, right? Use this to shape the rewards that you otherwise wouldn't normally. Okay, to summarize, we saw a couple of examples. Instruction following, where the instruction is inherently important to the task. We have to follow these instructions. Embodied question answering, extending VQA to embodied setting, where you don't see the whole state and you have to move around before you see it. Reward shaping, where you're defining external rewards, sometimes through MTurk, sometimes through instruction manuals to help you, and domain knowledge as well. Domain knowledge, usually instructions manuals also a good form of domain knowledge. And nowadays, there's several other challenges. Nowadays, really learning from open-ended manuals is possible, right? You saw the example with Civilization, where there was a lot of manual parsing of the sentences, parsing of what is a state description, what is an action description. Nowadays, with language models, you can probably think of several open research questions on using language models to automatically parse these open-ended rewards. Right? Some of these language models can take in almost the entire context of a very long instruction manual, perhaps even a textbook. And when you start asking questions about it, it's still going to give reasonable answers picking up relevant pieces of information from the manual. And here's an example for Atari, right? We have all these Atari games. The Pong was one of them. Breakout is another classic example. The Pac-Man was also one of the examples. And you have all these long instruction manuals telling you what to do, who are the enemies, how to get rewards, and so on. Another big area of research is text-based games. Reinforcement learning is always a debate between, do you want more realistic, human-like, so you have people working on habitat, like real-world homes, getting robots to clean up your homes. And you also have people who complain that the real world can be too simple, so they go into like text-based games. And these text-based games can be arbitrarily complex, right? Because you can automatically generate them with multiple levels. I don't know if people have played text games. Like you have a setting, and then they ask you, should you go left, should you go right, should you pick up the book, should you fly here, fly there, and this can have very, very, very long exploration problems. So it's not very realistic, but it really goes to the core of some of the technical challenges in RL. For example, sparse rewards, long-term rewards, and finally learning from lots of offline data. Right, we've looked at a lot of reinforcement learning being online in the setting that you have the environment, you're exploring that environment, and you're kind of going through seeing which states and rewards are good. Also, lots of interest in using lots of offline data, right? Can you play Minecraft, for example, by watching human videos of people playing Minecraft? So here's an example of a paper that collected such a resource. And finally, cases where it's hard to specify rewards. We've always been in this paradigm where we knew what the rewards were, or we were able to shape the rewards. Sometimes it's really hard to specify the rewards. It's only easy to specify the final goal. For example, just clean the house, right? You want to build robots eventually for household or for schools, for hospitals. Just clean the house, clean the hospital. You don't want to say, oh, put this here, put this there, put this here, right? So how can you essentially go from very high level goals to these more fine-grained explanations of what to do, and language models is an opportunity for that. All right, so that's a wrap up. We've looked at structure. Today we looked at more interactive structure, and on Thursday we'll see a sampling of all these other types of structure, concepts, inference, and external knowledge. All right, thanks everyone.